we'll move on to Will Usher. And so Will's now a graphics software engineer at Intel, but I think the work he's going to be presenting just now was done while he was at the University of Utah as on the graduate program. Is that right, Will?
Yeah. So can you see my slides here?
Got it. Yeah.
Okay. Yeah. So I actually now work with Dave DeMarle, who gave a talk earlier at Intel. So we're working on the Osprey project. But this is some work that I did during my PhD, and I'm still, kind of continuing this with some other colleagues on the side, since I think this is a very exciting, future for how we can make scientific visualization of large-scale data more accessible. So this is actually work that I presented at LDAV last year. So, to answer essentially the title of the talk. It is actually a fact that we show in the paper that, this kind of messy looking surface is actually an isosurface of this 1 terabyte volume. And using our approach, we can compute this surface in 576 milliseconds in Chrome on an RTX 2070, which is a consumer GPU that only has 8 gigabytes of memory, compared to our baseline, which was to use VTK to compute the surface using VTK's parallel isosurfacing algorithms on the CPU. And that still takes 78 seconds and 1.3 terabytes of RAM on a quad socket Xeon server. So quite a big difference. If you make the right algorithmic choices to work with the data, you can actually bring very large scale data viz down to small scale consumer platforms, which I think is going to be valuable as people's data sizes continue to grow. We still need some practical way that a scientist can access their data and visualize it. So, we'll look at kind of why would we want to bring, visualization of large scale data to the client side. And so one benefit is that we have a standardized cross-platform deployment environment. So essentially the browser becomes our portability layer, which is nice. It's also widely accessible to users. They don't need to compile anything from source or download, a bunch of packages, install things on their systems. They just need their web browser. So it's also nice for more secure environments where people may not be able to install things on their own system. By moving things to run fully on the client side, so there has been work in Viz on rendering large scale data, say on like an HPC system or server, and streaming this back to the user in the browser. But you can have latency issues and other issues that I'll discuss later with this. By actually doing it in the client, we're able to provide low latency interaction, and it's easier to work with data sets that people may have locally on their system. And finally, when it comes to considering the cost of deploying something, if we're considering trying to make scientific visualization as accessible as information visualization applications, which just run in the browser and are accessible to say potentially millions of people who have seen this COVID dashboard from last year, running a large number of backend compute servers to render and process the data can get extremely expensive and potentially prohibit the ability of someone to deploy a large scale visualization application on the browser just due to the cost that would be incurred. So prior work has looked at deploying SciViz apps running on the client. Though at the time there are issues with the browser ecosystem that limited these in the scope that they could achieve. So maybe it's kind of special purpose or maybe like smaller applications or demos that are kind of custom built. So you would use basically WebGL for rendering or doing some processing. Although WebGL only provides a graphics API, you typically lose access to native libraries that you might rely on, like VTK, which we kind of take for granted when we're working natively, that VTK will be available and provide a large number of algorithms that we need. And porting things to JavaScript, usually we find that the performance of JavaScript is subpar, but by running things locally, we can alleviate the latency that the user might have and provide a more interactive application. On the other hand, we can use a server for remote processing. So we have access to pretty much as much compute as we have money. So we can run very large scale systems. And we have access to all the native libraries and code environments that we're used to working with. However, we can start running into issues with latency for user interaction and costs of running these servers. So as I was hinting at, there's quite a few challenges that are still faced when considering bringing sci-viz of really large scale data to the browser. So we don't have access to these widely used libraries, even basic things like VTK or libtiff, things that you just expect to exist on a desktop environment. JavaScript performance is improving as the browsers work on their VMs, but it's really not comparable to native code. WebGL is only a graphics API, so there's no general purpose computing in there, like compute shaders that you might have in Vulkan or DirectX or CUDA compute kernels. So we're pretty limited, we're extremely limited in the amount of parallel computing that we're able to do. And WebGL, in terms of just rendering complex geometries or complex data sets, it lacks a lot of the features that we need for high performance rendering. However, there have been recent advancements in the browser ecosystem that I'll discuss that could actually help us address these issues. So WebAssembly is this bytecode format for a virtual machine that is implemented in the browsers. Actually today is available and can provide improved performance over JavaScript, and can be compiled to, you can compile native code targeting it. And I'll discuss briefly a few examples of that. And in terms of high performance graphics and general purpose GPU computing, WebGPU is actually an upcoming graphics API for the browser that I think is targeting their 1.0 spec by the end of this year or maybe early next year. But it is becoming available for testing in Chrome Canary and Safari and Firefox. So there's buy-in from the major browser vendors to implement this API. And it gives you access to the powerful capabilities of modern GPU systems. So I'll just mention briefly the contributions of where we're going to end up to give some excitement of what's coming later in the talk. And so the main focus is really going to be on demonstrating how these technologies, specifically WebGPU in this case, can be leveraged to deploy powerful scientific visualization applications that run entirely in the browser and can work with massive data sets. And so this is done through a new GPU parallel isosurface extraction algorithm that operates directly on compressed data. The algorithm uses a GPU-driven memory management and caching strategy to allow us to work with these compressed data sets on the GPU without paging data back and forth from the CPU memory. And I'll demonstrate that this algorithm achieves interactive isosurface extraction on up to 1 billion voxels and 1 terabyte of volume data entirely in the browser. So just to revisit kind of where the browser ecosystem has been evolving to, WebAssembly is a bytecode format for a virtual machine that's integrated natively in the browser. And it's almost as fast as native code. There have been another paper profiling it on a bunch of different standard benchmarks, and it finds that if you compile these like C or C++ codes to WebAssembly, you're about 1.5 to 3.5 times slower than native code. WebAssembly also runs in this lightweight virtual machine, which can be embedded in other native applications. So you can actually compile kernels of your application to WebAssembly and share them across the browser and say a native version of your application. One really beneficial thing of JavaScript or of WebAssembly compared to things like Java applets and Flash is that it's embedded natively in the browser. You can target it from multiple languages, and especially when working with large data sets, you can actually share the memory space with JavaScript. So what I'm showing here is a small wrapper over the loss tools library for working with LiDAR data sets. This is compiled to WebAssembly. We have to provide a C API for that. And then we can just use loss tools to open an LAZ file, so a compressed LiDAR data set. And to access that data for rendering in JavaScript, we can just create a view of the WebAssembly module's point data. WebGPU, on the other hand, is a modern high-performance graphics API for the web. It supports compute shaders, storage buffers, storage textures, kind of standard things that we expect in a modern desktop graphics API. And it's available in the browser preview builds and is in development, targeting releases later this year. So I'll just discuss briefly like a few example sci-viz use cases to show kind of performance more on the WebAssembly side, since our later focus will be on WebGPU. So here we used the native libraries libtiff and loss tools compiled to WebAssembly to load TIFF files, say for a neuron visualization application in the browser, or to load LiDAR data sets to render them as points. And we find, similar to previous work, that these tasks are about 2 to 4 times slower for these sort of memory data processing intensive tasks. So compared to loading the TIFF file natively on the desktop, it will take about 2 to 4 times slower in the browser, and same for the LiDAR data set. So there's some impact from moving into WebAssembly, but it's not like a 10x penalty. On the other hand, compute tasks can be accelerated somewhat better by WebAssembly because there's less memory operations that have to be still checked by the WebAssembly runtime. So this is just a textbook serial marching cubes. And we find that on these small data sets, it's just 1.5 times slower in Firefox, and at the time was 3.2 times slower in Chrome. And finally, to evaluate WebGPU, we implemented just a textbook data parallel marching cubes and compared it with a native Vulkan implementation of the same code. And so while we don't see much of a performance improvement on the Surface Pro 7, which is just running an integrated GPU, we do see performance improvement compared to our serial version on the RTX 2070. But what's also more exciting to see here in terms of evaluating the impacts that we might pay for moving to WebGPU is that the performance difference, or there's not much performance difference between the Vulkan and the WebGPU code as we get to the larger data sets. So like on the fuel and the hydrogen, these small data sets, we pay maybe some overhead penalty, but this starts to get hidden or vanish as we move to larger data sets that we care about. So I'll now talk about our approach for GPU parallel isosurface extraction on block compressed data using WebGPU. And the motivation is really that we need practical and accessible ways for scientists to visualize their data, even as the sizes of these data sets continues to grow. And so this is achieved through our work here. So I mentioned just briefly a very abbreviated summary of prior work on parallel isosurface extraction. So Daikin et al. Presented a GPU-based method built on prefix sums and stream compactions to compute the vertices in parallel for each block using histopyramids. And this computational approach of prefix sums and stream compactions forms the foundation of most existing methods today, although you'd use CUDA for your kernels and Thrust or VTKM for your parallel primitives. Schroeder et al. Presented flying edges, which processes the edges in parallel to efficiently output a index triangle mesh rather than a triangle soup. And finally, Liu et al. Used a block-based work decomposition, which is similar to our method, where given the 3D volume, blocks of voxels are processed by thread groups, which are shown as these blue bricks here. And then within each group, a thread is assigned a dual cell, so the purple here. However, they assume that the entire volume can be stored on the GPU in a single 3D texture, so they're limited by the GPU memory. And they only use the block decomposition to accelerate the computation by skipping blocks that do not contain the isosurface. So our algorithm is motivated by 2 observations. So the first is that the isosurfaces that tend to be of interest to users occupy very sparse subsets of the volume. So if we consider here the amount of data that the surface actually touches, it's a small fraction. Actually, it shows here 11% of the actual data set that we really need to touch to compute the surface. And when people are interacting, they're usually exploring neighboring ISO values, or as we move this slider up and down, the individual surfaces that we see in this animation are not large jumps from each other. So if we decompress and cache the blocks that we need to compute one surface, we will probably need those blocks again to compute the next surface that the user wants to see. And that will help us reduce the amount of decompression per computation that we have to do. So our algorithm, block compressed marching cubes, or BCMC, as I'll say throughout the rest of the talk, decompresses, caches, and processes only blocks that contain the surface to minimize its memory footprint and accelerate computation. And the computation is further accelerated by moving this entire pipeline to run on the GPU. So all steps shown here are run in parallel on the GPU. So I'll first give a high-level overview of the algorithm, and then I'll discuss the key components in detail. So the cache contains a growable number of slots within which a decompressed block is stored. So starting from the previous surface or an empty cache, we want to compute the new surface shown here in A. The first step is to find the blocks that contain the isosurface or are otherwise needed to compute it. The LRU cache update determines which of these blocks are already in the cache and which ones have to be newly decompressed and added to it to compute the surface. This GPU-driven caching strategy is what allows the algorithm to work with compressed data directly on the GPU, and I'll discuss this in more detail shortly. Then steps D through G find the active blocks that are going to output vertices and computes the isosurface on them to output a triangle soup. So BCMC stores the value range for each 4-cube block of data, which is used to check if a block potentially contains the isosurface. So that would be these blocks. However, since BCMC never stores the entire decompressed volume, it's not sufficient to only decompress the highlighted blocks. That's because if we remember learning about marching cubes, it's that the dual grid of each block shares vertices with its neighbors on the positive side. So the block A here needs data from its neighbors B, C, and D to actually compute the isosurface. So a block is actually marked active if the union of it and its neighbors' ranges contain the iso value. So to compute the surface here, the orange dashed line, we'll have blocks 0 through 5 and 8 as active blocks that we have to potentially decompress that need to be available to compute the surface. The GPU LRU cache then performs on-the-fly decompression and caching of blocks. So given the previous cache state, we need to decompress the new highlighted block and add it to the cache. So that's 8 here. The cache state and update inputs are all stored on the GPU so that the cache update can run entirely on the GPU in parallel. So we don't have to upload any new information or read back any data, so that we can minimize the amount of data transfer over PCIe and the amount of synchronization that has to happen with the host. So the cache itself stores the decompressed blocks, while the other buffers tracked for the cache store information about a block's location in the cache, its age, occupancy of the slots in the cache, and so on. The list of active blocks are those that we marked active in the previous step, where 1 marks an active block. And finally, the entire ZFP compressed volume is stored on the GPU so that blocks can be decompressed on the fly without having to upload any new data from the CPU. So the LRU cache update is executed entirely on the GPU through data parallel primitives. The first step is a GPU kernel that increments each slot. Next, a thread is run for each block to mark new blocks that must be decompressed and which current ones can be evicted. Cached blocks that are active have their age reset and the slot marked as unavailable. So we don't want to evict a block that we need to compute the new surface. This is the case for all the blocks that are shown in this example as well. Blocks that are cached and inactive. Oh, sorry, I have a very important phone call that I have to take here. 1 second. Giving this talk though. Yeah. So sorry about that. I'm still on this. Sorry, this is very, very important phone call. Anyways, so slots that are so for blocks that are uncached and active, we mark them as new. Yes. So GPU prefix sums and stream compactions are then used to compute lists of new block IDs and available slot IDs. And at this step, we see how many slots we need in the cache. And the cache is grown if more slots are needed than are available in the cache. Finally, GPU sort by key orders the available slots by decreasing age to evict the older blocks first, so that the blocks that have been least recently used will be overwritten first if we have to evict a block. Next, a GPU kernel assigns new blocks to available slots in the cache. where any previous block in the assigned slot is evicted. Eviction is done by simply overwriting the data and setting that block's index to -1 to mark that it's no longer cached. And the last step decompresses blocks into their slot using a WebGPU port of ZFP's decompression kernel. So we took their CUDA version, ported it to GLSL, and run it in WebGPU. So we conducted an extensive performance evaluation of our algorithm. So the evaluation is run on 9 different data sets ranging in size from 67 megabytes to 1 terabyte before being encoded and compressed. And the benchmark covers data sets that are in size from 16 million voxels up to 1 billion voxels. We also evaluate on both nested and turbulent sheet isosurface types. And these have different cache behaviors. So that's why we pick these 2 different models. A nested isosurface is like a typical in MRI scans, where you have the lower ISO values contain the surfaces at higher ones. So you can kind of have this surface coming in some sense. And so you'll have much cache friendlier behavior on these data sets, because the blocks that contain the surface tend to overlap and share and reuse a lot of data across this due to this containment property. On the other hand, the turbulent sheet isosurfaces are more like a crumpled sheet that's moving through the domain. These would come from various turbulent simulations, like the 2 shown here, which are turbulent fluid flows. And these tend to be much less cache friendly, as the surface doesn't really share a lot of blocks. As you change the ISO value, as you sweep it, it will move through the domain. So there's less reuse of blocks. And the turbulent nature of the surface tends to touch a large number of blocks. So random ISO value selection tends to be require much more decompression. And so we test 3 ISO value selection modes that are typical of common user interactions. So picking random ISO values, sweeping the ISO value up or sweeping it down. So random ISO value is like you're trying to find what's interesting to you, and then sweeping it up or down is when you're trying to explore neighboring values in the data. And the ISO values that these are selected on, we run these benchmarks on 100 different samples of ISO value, and we select the value range based on a subrange of interest to users. So we won't run the benchmark on like noise values or an ISO value that's so high that you don't compute any surface, because they're not interesting to test. So BCMC allows computing isosurfaces using a small fraction of the original dataset size. So on the left, I have 3 nested surfaces that we tested on, and on the right, the 2 turbulent sheet surfaces. These dataset sizes range from 650 megabytes up to a terabyte, and they're encoded in both precision and resolution. So the first 4 volumes are just compressed with ZFP, and the last volume is also compressed using state-of-the-art precision and resolution encoding to reduce the resolution as well. Now, if we look at the GPU cache size that we have, to compute the surfaces on the left, we need about 4.5 to 5% of the blocks to be decompressed. So our cache is only 70 to 227 megabytes, giving us data size reductions of 4.8 to 9.3 times. The turbulent sheet surfaces tend to have much more blocks be active for any given surface. So here on the Miranda, we have 26% of blocks that are active, and requiring a cache of 1.1 gigabytes. So this just gives us a reduction still of 3.9x, which is quite substantial. And on the last data set, we have 0.28% of blocks active. This is compared to the original resolution. So we need a cache of 1.4 gigabytes, and this gives us a reduction of 690x. So the picking random ISO values gives a very cache unfriendly workload where we're jumping around the data set itself. However, even on this cache unfriendly workload, the nested isosurfaces still see very high cache hit rates. So 91 to 99%, as I mentioned, due to the kind of structure about the topology of those surfaces. And so our computation on the RTX 2070 ranges from 100 23 milliseconds per surface on average to 372 over 100 surfaces. And on a very low-end device like a Surface Pro 7, this takes 320 to 1.3 320 milliseconds up to 1.3 seconds. The turbulent sheet surfaces are a bit too large to run on the Surface Pro 7 since it only has 3.8 gigabytes of RAM. However, the RTX 2070 computes these in 2.2 to 2.6 seconds. And as I mentioned, the turbulent sheet surfaces are much less cache friendly. And so we see poorer cache hit rates on the random isosurfaces. However, sweeping the ISO value up or down provides a very cache-friendly interaction mode. And we see relatively high cache hit rates across all the data sets. On the RTX 2070, again, we average about 138 to 343 milliseconds. On the Surface Pro 7, 401 milliseconds to 1.5 seconds on the nested surfaces. And on the turbulent sheet surfaces, 550 to 907 milliseconds. So I'll wrap up with just a brief kind of roadmap of challenges that we're facing and that we should focus on to make it easier to bring scientific visualization to the browser. So I hope by now that through this talk, I've convinced you that the browser is becoming a very capable platform that we can deploy powerful scientific visualization applications in and deliver them to scientists who can use them effectively on their different systems, and that if we make the right decisions about how we design our algorithms and how we process the data, we can process very large data on small client devices that are typical that a scientist might have. And however, there's quite a bit of work to be done. So one thing that would be extremely valuable is a community effort to recompile standard libraries to WebAssembly. So something like VTK has a number of dependencies that it pulls in. And so the problem when you start building something for WebAssembly is that all of the dependencies you link also have to be compiled to WebAssembly and linked. So you get kind of this huge explosion. So this can actually be quite a bit of work to track everything down and recompile everything. So a community repository would be extremely beneficial so that people don't have to repeat this same work. And then people have discussed VTKM previously in this workshop. And when you're on WebGPU, you're basically on your own when it comes to parallel primitives. And so one issues that we have in this method is that the sort and scan and data parallel primitive performance could be much better if we use something like VTKM or Thrust, where there's these highly optimized implementations available. And so it would be very valuable to have something like that ported to WebGPU to make it available to end users or other visualization researchers. Yeah, so that's the end of my talk. I can take any questions. The paper from LDAV is available at my website. You can email me here or contact me on Twitter. And if we have time, I can actually show like a little live demo. If you have Chrome Canary installed with WebGPU enabled, you can go to these URLs and actually run some of these demos. So I can let me get this up since I think we do have a few minutes.
Yeah, go ahead.
Yeah. So, okay, I think you should see the web browser here. Yeah. So this is the magnetic reconnection. And so this is running on a Mac Mini with the M1 CPU. So you can kind of change the surface around or come in, and you can try these out as well. So this data set is 512 cubed. The skull is a 256 cube one. And so, yeah, I can take any questions then.
Okay, thanks very much, Will. Super interesting. There may be some questions coming in on the Q&A. I was going to ask about the WebGPU rollout. You're fully confident it's coming later this year. It's all going to be standard. I've been sort of caught out with things like WebGL2 is coming on Safari, whatnot.
Yeah, I don't know. I mean, they're confident. I went to some Chrome like seminar where they were talking about their plans, and they're like, okay, we're targeting 1.0 spec like the end of the year. I feel like whenever a working group says like we're targeting this date, you might want to add a couple months to the date just to see. What I also find is that Chrome's implementation tends to be the furthest ahead compared to Firefox or Safari. So I think Chrome might have something, pretty usable at that point coming out. But in terms of like a general accessibility, it may be like mid next year or something. I hope that this starts becoming something that is just in people's browsers. But they're working quickly towards like a 1.0 spec at this point. So I'm hopeful, but it's still on the way. Yeah.
That's good to know. I was going to ask also on because you're sort of you have to handle the cache yourself. It's a bit like the early days of GPU, GPU. So did you have some choices to make on block sizes that you were using, or even the cache that you were sort of allocating beforehand?
So the block sizes are kind of chosen for us. So we're using ZFP to compress the data. And so ZFP uses 4 cube blocks. So we just take what ZFP has, since it's easiest in the whole pipeline to work at that scale. Since our individual kernel will take the compressed data and give you a 4 cube block. So we're kind of building on ZFP's block compression that way. But yeah, it's very much like early days of GPU, where if you need a sort by key, you implement a sort by key. You need a scan, you implement a scan. That's why it would be very nice to have like VTKM but WebGPU, or Thrust but on WebGPU, where people don't have to re-implement so much of the parallel primitives that we take for granted on the desktop. Yeah.
But it's certainly extremely impressive that how far you can go with pulling these APIs together and putting them to one purpose like this.
That was kind of our thought, was like, now we have access to these real compute capabilities. So like, really, how far can we push it and see like where can we get with even what's kind of available in like a beta standpoint in the browser. And you can actually get quite far. So I'm excited to see what the state of web-based visualization will be like next year, as these get more stabilized and released, and people start really working with them. Yeah.
Garth, you've appeared. Did you have a question? No, just turn his camera on. Okay, well, we're a little bit over, so we'll stop there. Will, thanks very much.